in the previous module, I was talking about cyclobutadiene, and I said you that in cyclobutadiene system, you have 4 pi electrons, so 4 by 4 determinant you will obtain, and when we have written the x value, that we got the from the determinant we calculated the x value, and x was -2, 0, 0 and +2. 4 different value we got, and from these 4 different values we can obtain the energy value also. So, if you obtain write x is equal to -2, then the energy you get E1 is alpha plus 2 beta, and this is for the bonding molecular orbital, the lowest energy, because both alpha and beta are negative quantity. I am saying it time and again. Okay. And if you have x is equal to 0, then the energy will be E2 will be alpha for non-bonding molecular orbital, and again E3 will also be equal to alpha, because this value is also 0, x is equal to 0. So, E3 will also be alpha for non-bonding molecular orbital. If you take +2 value, then E4 becomes equal to alpha minus 2 beta for anti-bonding molecular orbital. This is a mistake. For anti-bonding molecular orbital, you just make a correction, anti-bonding molecular orbital. Because you obviously you look at this value, it's alpha plus 2 beta, and both alpha and beta are negative, so this will be more negative. But this will be one of the term will become positive, because beta is negative and this is a negative sign, so one of the term will become positive. So it will be anti-bonding molecular orbital. Okay. It means that if you have 4 different electrons, then 2 electrons will go to the bonding molecular orbitals, but rest of the 2 electrons will be in E2 and E3. One of the electron in E2, another electron in E3. So this will be the picture of energy diagram, like this one, energy diagram. So lowest energy E1 is alpha plus 2 beta containing 2 electrons, and then E2 energy is equal to alpha, E3 energy is equal to alpha, and so each of these will contain 1 electron, and E4 will be unoccupied molecular orbital. Okay. If you calculate the energy E pi of energy pi of these pi electrons, what you will get? 2 electrons are in E1, so 2 into alpha plus 2 beta and plus 2 alpha, because here this is also alpha, this is also alpha, so 2 alpha is the energy. So total energy E pi is equal to 4 alpha plus 4 beta. Okay. Now, if you calculate the delocalization energy here, the delocalization energy is 0 here. You do not get a delocalization energy. So in contrast to butadiene system, in butadiene system, a straight chain compound, we got some delocalization energy. But in this case, cyclobutadiene, we do not get any delocalization energy, because the total energy of the E pi system is 4 alpha plus 4 beta, and 2 ethylenic bond will again give you the same energy, 4 alpha plus 4 beta. So this delocalization will not give you any energy. Okay. The next task after finding out the energy is finding out the wave function or eigenfunction for the system, and for that what you need to know is HMO coefficient for cyclobutadiene. Again, if you have a 4 by 4 determinant, you will add first the equations with respect to each of these raw in the determinant. So what will be the first equation? First equation will be A1x plus A2 for x is equal to -2 I have written. So instead of writing the A1x, I have written -2A1 plus A2 plus A4 is equal to 0. Okay. Then the second equation will be A1 minus 2A2 plus A3. Obviously, the second row will give you this equation, A1 minus 2A2, x, you have 1 x 1 0. So 0 I will omit everywhere, and then you have A1 A2x plus A3. So A2x will become minus 2A2. Okay. So this is the second equation. Then you have the third equation, that's A2 minus 2A3 plus A4 is equal to 0, and the fourth equation will be A1 plus A3 minus 2A4 is equal to 0. For x is equal to -2, you have these simultaneous equation written from the coefficients. Now what we do, multiply equation 1 by 2 and then add it to equation 2, then add to equation 2. So if you multiply by equation 1 by 2, then it will be minus 4A1 plus 2A2 plus 2A4. Okay. And then if you add the second equation, that is A1 minus 2a2 plus a3 is equal to 0. So what do you get? Because both equations are equal to 0, so finally you will get 0 whether you add it or do whatever. So what you get? Finally what you get is minus 3a1 plus a3 plus 2a4 is equal to 0, and then subtracting equation 3 from equation 1, subtracting equation 3 from equation 1, the equation 1 is minus 2a1 plus a2 plus a4 is equal to 0, and equation 3 is equation 3 from equation 1. Okay. So minus a2 plus 2a3 plus a4 is equal to 0. So what do you get? You get minus 2a1 plus 2a3 is equal to 0. Wait. a4 and a4 will go. Okay. And then it is minus 2a3, so it will become plus, and it's equation number 3. So minus a2 plus this one and minus this one. Okay, we have subtracted, so minus sign will go. So a2 and a2 will go, and you have minus 2a1 will remain there, and this a4 and a4 will also go, and this a2 will go. Minus 2a1 plus 2a3. This is the only remaining term. Minus 2a1, if you subtract, and this term will remain. So minus 2a, rest of the term will go. Okay, and you have minus 2a1 plus 2a3 is equal to 0. And then what does it mean? 2a3 is equal to 2a1. It means a1 is equal to a3. So what you get is a3 is equal to a1. For x is equal to minus 2 I am talking about. Okay. So this becomes equal to a3 is equal to a1. Using this equation, what we do? I can write minus 3a1 plus a3 plus 2a4. This is which equation? Minus 3a1. Using this equation, what you can write is minus 3a1 plus a3 plus 2a4 is equal to 0. So you have a1, a3 and a4, and if you look at the a1, a3, a4 terms, a1, a3 and a4 terms, these are the terms a1, a3 and a4, and you have a1, a3, a4 terms are this one, the last equation. So you can write this one from where? Okay. A3 is equal to a1, so a3 is replaced by a1, and 2a4 you have, and what does it mean? It means if you subtract this one, what you get? 2a4 minus 2a1, and so a1 is equal to a4. We got a1 is equal to a4. From equation 1, again you can write 2a1 plus a2 plus a4, so it is 2a4, because a1 and a4 is same, so minus 2a4 plus a2 plus a4 is equal to 0. So what do you get? You get a minus a4 plus a2 is equal to 0, and a2 is equal to a4. So you get a2 is equal to a4. Now you see, all a1, a2, a3 are equivalent. Okay. So a2 is equal to a4, a1 is equal to a4. So this is equation which is important. This equation we obtained, and we also obtained a1 is equal to a3. Okay, a3 is equal to a1, or same thing. a1 is equal to a3, a1 is equal to a4, a2 is equal to a4. So all are equal. Okay. Now we will go for, obviously, normalization condition. That will be very easy because everything is equal. So it will be 4a1 square is equal to 1. Look at the normalization condition. From normalization condition, what you have? a1 square plus a2 square plus a3 square plus a4 square is equal to 1. And if that is so, then you have 4a1 square is equal to 1, and you have a1 is equal to 1, a1 square is equal to 1 by 4. So a1 is equal to 1 by 2, and all a1, a2, a3, a4 are equal. So all a1, a2, a3, a4 value will be equal to 1 by 2. Okay. So all values are equal. For x is equal to minus 2 bonding molecular orbital we are talking about. Okay. And with this, what you can write is the wave function, eigenfunction for the bonding molecular orbital psi 1 is equal to 1 by 2 p1 plus p2 plus p3 plus p4. Okay. So the first wave function we obtained. Now Thereafter, the x value which we have is 0, and you have, so if you write the equation will be like this one, simultaneous equation: a2 plus a4 is 0, a1 plus a3 is 0, a2 plus a4 is 0, and a1 plus a3 is 0. Okay. So again, what you have? Degenerate set of orbitals, and we may arbitrarily choose one coefficient, as we did in the case of cyclopropenyl system. Whenever you have a degenerate set of orbitals, this is the way by which you do find out the value of coefficient. That you choose one coefficient arbitrarily, and then for the next coefficients you use the orthogonality and normalization condition to get the other coefficients. Okay. So this we have done earlier in cyclopropenyl system. Now suppose a2 is equal to 0 here. If a2 is equal to 0 here, then a4 from the equation number 1, a4 will also be equal to 0, and if you use the normalization condition, then a2 and a4 are 0. So what you get? a1 square plus a3 square is equal to 1, and we can write a1 is equal to 1 over root 2, and a3 is equal to minus 1 over root 2. Both will be equal. Okay. a1 plus a2, so it will be like this one. And then the coefficients which you can write as psi 2 is equal to 1 by root 2 psi pz1 minus psi pz3. This we can write. Okay. If it is so, because if you have, you should not have any confusion here. a1 plus a3 is equal to 0. So a1 is equal to minus a3. Okay. So if you square this one, it will be a1 square. Okay. If you put value here, a1 square plus minus a1 square, so it will be 2 a1 square is equal to 1. So a1 will be 1 by root 2. It's very simple. That's why I will skip this. And now you have psi 2 is equal to 1 by root 2 psi pz1 minus psi pz3. Okay. So we have the value of, for one of the, in one case. For the coefficient of psi 3, what you will use? You will use the orthogonality condition. Psi 2 we have done. For psi 3, if you have to use, then you will use the orthogonality condition, and this orthogonality condition is this one. Because psi 2 is, I have already found 1 by root 2 psi pz1 minus psi pz3, and then psi 3 we don't know. For psi 3 I have written a1, a2, a3, a4 coefficients. Okay. If you solve this one, and if you look at the just the similar terms, you neglect all the cross terms, because psi pz1 multiplied by psi pz2 integral will be an orthogonality condition and will become 0. So the only thing terms which will remain is pz1 terms and pz3 terms. So these and these will remain. Okay. So a1 and a3 term will remain. Rest of the thing will become equal to 0. So you can write 1 by root 2 a1 minus 1 by root 2 a3 is equal to 0. And if it is so, then you write 1 by root 2 a1 is equal to 1 by root 2 a3, and it means a1 is equal to a3, and if a1 is equal to a3, then a1 plus a3 is equal to 0, that you know. So and a1 is equal to a3 is equal to 0. So both a1 and a3 is 0, and a2 plus a4 is equal to 0. So a2 is equal to minus a4. Now here a2 is not 0. Here we are writing the equation, simultaneous equation, a2 plus a4 is equal to 0. So a2 plus a4 is equal to 0. So a2 is equal to minus a4, and again you write the normalization condition. From the normalization condition you get a2 plus a4, and so a2 and a4 will be 1 plus minus 1 by root 2. a2 and a4 will be 1 by root 2 and 1 by a4. So for psi 2 and psi 3, only two orbitals will participate. In case of psi 2, 1 and 3 have participated. In case of psi 3, 2 and 4 will participate, and the normalization and the eigenfunction which I will write is 1 by root 2 psi pz2 minus psi pz4. In contrast to psi 2, where I have written 1 by root 2 psi pz1 minus psi pz3. So pz1 and 3 was there in psi 2. In case of psi 3, you have psi pz2 and psi pz3. Okay. This is how we differentiate the different molecular orbitals. Okay. Now for x is equal to plus 2, that is the antibonding molecular orbital. Again we write the four equations from the circular determinant: 2a1 plus a2 plus a4 is equal to 0, and all equation is numbered. This you have already done, and here you have plus 2 sign, so the no negative sign you see here, because x is equal to plus 2, and then multiply equation 1 by 2 and subtract equation 2, the similar way as we did for x is equal to minus 2. So what you get is 3a1 plus 2a4 minus a3 is equal to 0, and then subtract equation 3 from equation 1. So if you do that, you get this one, and finally what you get is a1 is equal to a3. a1 is equal to a3 you get, and if you get a1 is equal to a3 and do the further, put the value further in the equation, simultaneous equation, you will see that it will be minus a2 plus minus a4. Okay, a1 is equal to a3 you get from here. 2a1 minus 2a3, if you put this value here, what do you get? a1 and a3 are same. Okay, so a1 and a3 are same, it will be 2a1 plus 2a4 is equal to 0, and so it will be minus this one. Okay, now once we have this one, then 3a1 plus 2a4 minus a1 is equal to 0. So you can write 2a1 plus 2a4, because 3a1 minus a1 will be 2a1, and then you will have a1 is equal to minus a4, and so obviously if you put this value in question number 1, you get a1 is equal to minus a2. So finally what you get is a1 is equal to a3 is equal to minus a2 plus a4. From these equations, it's obvious. Okay, and if you have this one, then go for the normalization condition. a1 square plus a2 square plus a3 square plus a4 square is equal to 1, and you have negative values, so a square will become positive, and it will be all 4a1 square and 4a1 square. So a1 will be equal to 1 by 2, and so a1 and a3 are equal, so 1 by 2, and a2 and a4 are equal, so minus 1 by 2. So the only difference between psi 1 and psi 2 is of sign. The coefficients remains 1 by 2. Okay, for a1 and a3 you have positive sign in the psi 4, and for a2 and a4 you have negative sign. But in case of psi 1, the coefficients is 1 by 2, and everywhere it is positive. Okay, so the wave function finally is psi 4 is equal to 1 by 2 psi pz1 minus 1 by 2 psi pz2 plus 1 by 2 psi pz3 minus 1 by 2 psi pz4. Okay, so all 4 eigenfunctions we obtain, all 4 eigenvalues we obtain for cyclo-butadiene system. Okay, now extending this, if you look at these energy values and eigenfunctions, these are the energy values. From lowest one energy is alpha plus 2 beta, this is your bonding molecular orbital. Then you have these two non-bonding molecular orbital, which is degenerate. These are degenerate set of orbitals. Degenerate set of orbitals, and this is your anti-bonding molecular orbital. Okay, so these 4 orbitals we got. Now thereafter, what we will do? We can write these equations again in a particular format, cyclic format, and where I say I have written it for the cyclopropynyl system also. And what I said you, that if you consider the plane of the board to be the plane of the molecule, then above the plane of the board and below the plane of the board are the lobes of pz orbital. And if a person looks from top, he is able to see only one of the lobe. He cannot see both the lobes of the p orbital, because he is looking from the top. So only one lobe will be visible to him, and that is what is the representation in this form is written here. For psi 1, all the coefficients are positive. Okay, so the positive lobe will be on the top, and he will be observing for all C1, C2, C3, C4 the positive lobe only. Okay. Another thing is, here we don't have it, but if you have the quantitative value of the coefficients different, then you can increase the size of the circle also. Okay, on the each carbon atom, filled circle or empty circle. Empty circle indicates the negative lobe of the pz orbital. Okay. Now for psi 2, you do not have lobes at the C2 and C4. Only C1 and C3 lobes is there, and one of the value is 1 by root 2, another is minus 1 by root 2. Okay. So if you go from this end to this end, you observe a nodal plane, because the wave function sign changes. or you go from here to here, here also you have a nodal plane. So the nodal plane will be at the center between the two, and the center is C2 and C4. So this is your nodal plane for the Cy2 system. Okay, this representation is done for the cyclic system. Another is also there. I will talk about that. Okay, then you have Cy3 system. You have C2 and C4, and see the in case of Cy2, you have one of the lobe is filled with the blue and another lobe is empty. So this lobe which you are looking at a positive lobe, this lobe you are looking at negative lobe. So it's a positive lobe, lobe of pz orbital, and here it's a negative lobe of pz orbital. Empty means negative lobe. So the same thing here also. You have a negative sign here, you have a positive sign here. So if you go from C2 to C4, in the mid you will have a node. If you go from C2 to C4 through C3, then in the mid you will have a node. So the node, this dotted line indicates the nodal plane of the molecule. Okay. Then again you have Cy4 system, where you have C2 and C4 coefficients is negative and C1 and C3 coefficient is positive. So you get positive lobe at C1 and C3 and a negative lobe at C2 and C4. Okay. And again you look at here, if you go from C4 to C1, there is a change in the wave function sign. So in the middle you will have a node. Then if you go from C4 to C3, then here also you will have a node, because it's minus half, it's plus half. See, from C4 to C3 also the change of wave function. From C3 to C2, again plus 2 minus, so a node is here also. From C2 to C1, again a change in sign, minus to plus, so you have a node here. So this indicates the nodal plane, and I said you the positive lobe and negative lobes and the base of the nodal plane. Okay. So the dotted line is base of the nodal plane, a positive lobe is solid fill, and a negative lobe is empty, no fill. Okay. So this way we represent the HMO of cyclobutadiene molecule. Now if you have the wave functions, if you have the then very easily what you can do is you can calculate the bond energy, bond order, electron density and charge density. That I have not done knowingly, because I have done it for the previous systems, and that will be a monotony of doing everything. So you try to find out to do it yourself, the electron density and charge density and the bond order for the cyclobutadiene system. Okay, that's a homework for you. So a homework for you is calculation of electron density, charge density, and bond order. Okay, for cyclobutadiene system, which I have not done it. You please complete it. Okay, it's not here in the slide. Now the next and the last system which I will do is again I will rush through this, is the benzene molecule, because we have not done any of the aromatic compound. So one of the aromatic compound is benzene system, and this, if you write the molecular orbital, then the 6 pz electron you have present on each carbon atom, C1 to C6, and you have a 6 by 6 determinant, and again this determinant you can write in the form of, now I have not written in alpha and alpha minus E form, I have directly written into x and 1. So if you just look at the first row, and the rest of the row you will do is equal to what? X. It will be x because the first one is H1 minus ES1 will be alpha minus E. So you can write x. H12 is bonded, so it is beta and it will become 1. 13 is not bonded, so 0. 14 is not bonded, so 0. 15 is not bonded, so 0. But 16 is bonded, so it's 1 again beta. Okay. So this is how we go for a 6 by 6 determinant. So with the, I said you earlier also that as the number of pi bond increases, the size of the determinant increases, and solving this determinant becomes more and more cumbersome. There are ways to do it in a more simpler way, but that uses the molecular symmetry concept. And since I have not done molecular symmetry, so I will not go to that concept. Those of you, if you are aware of the molecular symmetry and if you have done a course on the molecular symmetry, then you can go and consult any quantum chemistry book, and you will find that concept also, that how with the irreducible representation we can facilitate this calculation, factorization of this, finding out the value of these matrices and x values from this one. Okay. I have not used it knowingly because I am not doing molecular symmetry in this course. Okay. So if you do the factorization of this equation, then what do you get? You get different values of x, and the x value comes out to be -2, -1, -1, +1, +1 and +2. So you have, look at this one, -1, -1 and +1, +1. So you have two set of degenerate orbitals, one for the -1, another for the +1. Okay, and you have a bonding molecular orbital for +2, for -2, and an anti-bonding molecular for +2. So what will be the energetics here? If you look at the energy will be like this one, obviously. So this energy for x, if x is equal to -2, energy is alpha plus 2 beta. If -1, then alpha plus beta and alpha plus beta. See, these two are degenerate set of orbitals with the same energy. Again, E4 and E5 are the degenerate set of orbitals with the same energy, alpha minus beta and alpha minus beta. And for +2, you get alpha minus 2 beta, that is the highest energy, called anti-bonding molecular orbital. So these 6 different molecular orbitals you obtain, but for the highest one or for the lowest one, you have only one orbital, but in between you have two sets of degenerate orbitals. So what will be the energy level diagram for this? The energy level diagram will be something like this one. Okay, where you have bonding molecular orbital, then E1 and E2, E0 I have given for the ground state. So E1 and E2 is equal to alpha plus beta. Then E3 and E4 is same energy, alpha minus beta, and E5 will be alpha minus 2 beta. The number starts from 0, so it's 6 different kinds, say, energy levels. Okay, if you calculate the E pi value, then pi energy values, then pi energy values will be, you have 2 electrons here, you have 2 electrons here, 6 electrons, you have 6 pi electrons in the benzene ring. So 2 electrons in alpha plus 2 beta, and 2 electrons in alpha plus beta, and again 2 electrons in alpha plus beta. Okay, so both the degenerate set is occupied here, and the total energy will be 6 alpha plus 8 beta. 6 alpha plus 8 beta. And so if you find out the delocalization energy, what do you find? 6 alpha plus 8 beta, and you have 3 ethylenic double bonds, means 3 into 2 alpha plus 2 beta. So finally, the delocalization energy is 2 beta here. You see, in cyclobutadiene, delocalization energy was 0. In case of benzene ring, you have a delocalization energy equal to 2 beta. So it's fairly a stable compound, and that you know because aromatic compound all of you must have done in your organic chemistry. Okay, so these calculations, these approximations, HMO approximations, gives you a result which you already have read into organic chemistry. Okay, and you say that benzene is stable because of the resonance and all those things. Okay, so if you have to find out the coefficients, then again you will write the 6 equations from the 6th row of the matrix, and from this, if you find out the equation, I have not found the coefficients here also. I have just skipped that because I have taken so many modules are for the HMO only. So I am skipping through this. You can find it out from the 6 equations I have given you, determinant I have given you, and from these you can find out the value of. Again, you will have to use the same principle which I used earlier for the degenerate level. But anyway, so the 6 energy levels which we obtain for the molecule is like this one. The eigenfunctions which we obtain for this one, psi1, psi2, psi3, psi4, psi5 and psi6. Again, this also could be represented in the form of this equation, this cyclic form, and you see psi1 is all 1 by root 6. If you go for this one, psi1 is all 1 by root 6 and all is positive values. Okay, So the psi 1 plot will be like this one. Psi 1 plot is this one. If you look at psi 2, then you have C2, C3, then C5 and C6. Look at this one. C2, C3, C5 and C6. C5 and C6 are negative quantity and C2 and C3 are positive coefficients. So you look at this one. C2 and C3 is positive coefficients and these are negative coefficients. Now if you go from C2 to C6, what do you get? You get a node here. If you go from C4, from C3 to C6, C1, 2, 3, 4, C4 to C5, this is your C3, this is your C2, and this is your C4, this is your C5. Okay. From C3 to C5, again you have a coefficient here. So if you, nodes here. Okay. So if you have a node, here it is a nodal plane. If you look at the psi 3, then you have all the three, all 6 coefficients. But see, on one side you have the positive low, on another side you have negative low. It means you have C3, C4 and C5 coefficients are negative. 1 by root 12 minus 2 by root 12 minus 1 by root 12. And look at the size of the sphere. This sphere and this sphere is not of the same size, because this is 1 over root 12 and this is 2 over root 12. So this sphere is bigger in size as compared to this one. The same happens with the filled sphere also. It's 2 divided by root 12, so it's slightly bigger, and it's 1 divided by root 12, so it's slightly smaller. Okay. And if you go for the functions, then you can see the function. The function for C3 is, you see, psi 1 is positive, psi 2 is positive, and then psi 3, psi 4, psi 5 is negative, and again psi 6 is positive. So that's what we have drawn. So you see, this is psi 6, and the psi 1, PZ1, PZ2 was positive, then 3 negative, and then again C6 was positive. So this is how. Now there is only one place where the sign changes. If you go from here to here, it's both negative, sign doesn't change. If you go from, let me write it, C1, C2, C3, C4, C5 and C6. If you go from C3 to C4, there is no change in the sign. C4 to C5, there is no change in sign. But if you go from C5 to C6, there is a change in sign of the wave function, so there will be a node. If you go from C3 to C2, then also there is a change in the sign. So only one place there is a change in the sign, so this will be the nodal plane. Okay. If you look at the other diagrams, then also you get the similar thing. Now here you look. You have a positive sign here, a negative sign here, a positive sign here, a negative sign here, a positive sign here, a negative sign. Alternately, everywhere in the last psi 6, you have a positive, negative, positive, negative. So everywhere you have a node on each of these arms of the benzene ring, each of the pi sigma bond which you say. Okay. So if you go for C1 to C2, there is a change in sign. C2 to C3, there is a sign change. C3 to C4, there is a sign change. C4 to C5, there is a sign change. So everywhere you have a node, and so all these nodal planes are there. Okay. So this diagrammatic representation is given in every book where you have HMO coefficients, and this is very easy to remember the coefficients which is obtained. Also with the size of the sphere, you can guess that which coefficients is higher coefficients, which is lower coefficients. Another way of representing the cyclic molecules is called, and then electron density I have calculated for these, and you find that everywhere the electron density is 1, and you know benzene is a neutral molecule, so pi electrons are distributed uniformly around the benzene ring. This is what is the message from electron density calculation, and obviously if electron density is 1, charge will be 0, and you know benzene doesn't have a charge. If you calculate the bond order, then this bond order of for C1 to C2 I have calculated is equal to 2 by 3, and rest all bond orders are also 2 by 3 that you can calculate. One example I have given you, and which indicates that all bonds in the benzene rings are equivalent, and this is in nice agreement with the chemical properties of benzene, because then we say that all the hydrogen atom present in the benzene is equivalent because all bonds are of equal have equal bond order, and even the pi electron density is very uniformly distributed. Okay. Another way of representing the cyclic molecule is Frost-Haskell circle mnemonics. This also is something which is very important, because it's very easy to remember with this diagram the relative values of energy you can guess and all those things. So what it says, it's applicable to cyclic polyenes. The ground state energy level is non-degenerate. Higher energy levels are doubly degenerate, and highest energy level is non-degenerate for n is equal to even molecule. In case of cyclic polyene, this is what we have observed, that all the ground state level, whether it was cyclopropenyl system, whether it was cyclobutane system, and whether benzene system, these three cyclic molecules we have done, and everywhere what you found is that ground state energy level is non-degenerate. And if you go for higher level, then you get a degenerate set of doubly degenerate set of orbitals. In case of cyclopropenyl system also we got. In case of butadiene also you got doubly degenerate system, and in case of benzene also you got two set of doubly degenerate set of the orbital you got in benzene. Okay. So this is the properties of cyclic polyene, and for this what is written is what we are going to learn is Frost-Haskell circle mnemonics. This is and with this diagram it will be very easy to write the eigenfunctions and remember what is the value. So in this, how do we draw this diagram? For the first thing which we do is that we draw a circle with the which is of radius beta, where beta is the resonance integral that you know. Okay. Then appropriate regular polygon is inscribed in the circle, so that one vertex is at the bottom of the circle. One vertex should be at the bottom of the circle. Each corner of the polygon corresponds to a carbon atom. For cyclopropenyl system, since one vertex has to be at the bottom, so in a cyclopropenyl system you have 3 carbon atoms. So what you will do? Equilateral triangle, upside down you will change the equilateral triangle, and then you will insert it into the circle. So that's what is the diagram here. You look at this one. This circle is of beta, the value of circle is beta, and then you inscribe a equilateral triangle, but you just upside down you convert it, and then you inscribe it, because this in each of these vertex will indicate one of the carbon atom. This is called Frost diagram for the Frost-Haskell diagram for the cyclopropenyl system. Now, same way, if for a butadiene system you cannot have a circle and you can draw a butadiene like this one. No, this we don't do. In the Frost diagram, what you have to do is one of the carbon atom has to be touch the bottom of the circle. Okay. So this is cyclobutadiene system, and now you see the circle has a diameter of beta. Okay. So this is not minus, this is 1 orbital giving alpha plus 2 beta, 2 orbital of L alpha, and then again 1 orbital of alpha minus 2 beta. Okay, so this talks about the degeneracy. These two are the equal energy, so they are degenerate orbitals or at the same energy level. Okay. Now, similarly, you can draw for the benzene ring also, and you get an energy 1 orbital for the alpha plus 2 beta, that's the bonding molecular orbital, 2 orbitals of alpha plus beta energy, then again 2 orbitals of alpha minus beta energy, and then again 1 orbital of alpha minus 2 beta. So these 3 cyclic system we have done, and these 3 Frost diagrams are with you now. Okay. So now if you draw a circle, and instead of this one you draw a pentagon, then what you can say, that the lowest energy will be this one, alpha plus 2 beta. The highest energy will not be alpha minus 2 beta, it is not at the top of the circle, it will be less than that. And in between also, if you have the degenerate orbitals, then this energy will not be equal to alpha, because it is not in the middle of the circle. Okay, it will be alpha plus something. So you can have a relative idea about the energy of the molecular orbitals in the cyclic polyenes system by the Frost diagram. Okay, so that is finishes this HMO approximation methods, and we talked about the molecular system in detail. So we started with simple molecules, then diatomic molecules, and then complex molecules in the HMO system. Okay, thank you.